The SAXS data treatment is very important to obtain a good accuracy in the result, particularly when you try to characterize nanoparticles. The first step of the data treatment is to transform an image detector into a SAXS diagram. So let's go on the computer.
With the small angle X-ray scattering technique, we obtain an image on the detector which needs to be transformed in diagram intensity versus angle. In the case of perfect spheric nanoparticles, the SAXS signal will give variform periodic oscillation corresponding to the diameter of the spheres. The diameter is related to the angle Q, which is also related to the sample detector distance. This distance needs also to be measured carefully. For transforming the SAXS rings into SAXS diagram, we also need to take care of the instrument geometry. In the case of perfect detector perpendicular to the direct beam, the signal will give perfect circles. But in most instruments, the geometry is not perfect and the detector is tilted. The signal will give complicated ellipse. One needs to determine that. Here is an example of an image where the detector has a tilt of only 5 degrees, and this moves the ellipse center. The principle of the geometric calibration is to measure one reference sample that produces rings at very well-known values, and to fit an instrument geometry on the image. Here you have two acquisition images from the Xeuss instrument for silver bayonet and Tetradecanol. We use these two samples daily for calibration of the instrument. Silver bayonet produces regular rings and Tetradecanol produces very fine rings. This is my preferred sample because it is very simple to prepare and very useful, especially at low angle configuration. By example, detector to sample distance of 2 meters. For this purpose, we use the pyFAI library, which is written in Python by the ESRF team. This tool integrates the image radial averaging and the image correction. I recommend to go on the pyFAI website for downloading, installing and reading the documentation. You will also find very detailed video describing all the process. Here you have a list of scientific publications describing this library. We have to notice that pyFAI has a special definition of the experiment geometry. Instead of using beam center position of the detector and tilt angles, pyFAI uses the position of the detector in the space. It is called point of normal incidence. This will give a pony file. One needs to remember that. To resume, for the image data processing, we need a detector image, a mask image representing the parts of the image we don't want to process, and a geometry parameter file. In the data process, for each pixel we will calculate the angle and averaging the intensity. Let's go for the demonstration. Okay, so here we are on the Windows 10 configuration. I will start with pySAXS. So pySAXS is our homemade software for SAXS data processing, and we integrate pyFAI into pySAXS, so you can find some shortcuts for pyFAI tools. I already explained how to install pySAXS, pyFAI with Anaconda Python. So let's starting with the calibration tools. Here we are on the pyFAI calibration tool interface. So the first step is to define the experiment parameters. So I will open a sample from the Xeuss configuration at middle distance, so around 120 cm. So here I will open a Tetradecanol sample. So my detector is a Pilatus Dectris 1M, and the wavelength, because we are at 8 kV. Next step. Here we are on the mask duo tools. So we can find the same duo tools here on the draw mask interface or on typing pyFAI draw mask on command line. With this tool, we will define the parts of the image we don't want. Here in pink, the tool recognizes the detector Pilatus 1M and the 10 strips and defines the bound between the strips. I can also open previously defined mask here, and let's see the dead pixel. They are, yes, they are masked. So I can also play with threshold value to search the dead pixel. I can also change the mask by using the two tools. Here, for example, I can change the beam stop mask. It's quite easy. And don't forget to save it. Next step, we are on the peak picking interface. The idea here is to click on the rings and the interface will try to extract the peaks from the rings. We have three tools. One will extract peaks beyond max value, the second will extract continuous peak, and the third one will extract just one peak. We have to click on the ring just one time. Let's play with the first. Here you can see the tool define all the peaks. I can try to refine that. Yes, it's better. So let's try with the second one on the second ring. Here we will define part of the ring. Here I can change the ring number, so I will give it all the same ring number and try to merge rings and sort. Okay, can re-extract, it's better. And on the last one, I will play the last tool. So here I just click on the ring to indicate where the ring is. This is the last step, the geometry fitting. So this tool will try to fit a geometry on the rings. We can see one ellipse and we have the geometry defined. So here we are exactly on 118 centimeters. So next step, it will process the integration. Here we have a display of the azimuthal image, and here we have the intensity versus the angle. Okay, and let's see how are rings. Determination, yes, it's quite good. So I will save that as pyFAI. Save and close. The second tool we can use is the pyFAI integrate tool. Okay, open. I will import the pony file. Here I can check the geometry with the pony configuration and in the more classical configuration. I will define the mask file. The radial unit, the number of points, and the propagation of error if I want uncertainties. So batch processing, which file I want to process, this one. Okay, so it's done. Let's see if here you can see I have a .dat file. I can open it, and you can see I have a 3 columns dat file, hue, intensity, and uncertainties. But nothing is displayed. That's why we develop this tool, radial averaging parameter, also to import the pony file. We have to define the number of azimuthal points, to define the mask, and click on the sample I want to process. Radial average. Okay. Here, display the data. I can save the preference here. Yes. We also develop another interface called Image Surveyor. The idea here is to display and do the image processing each time the instrument produces a file. So each time the Xeuss instrument do an acquisition, we check on the directory, and the radial averaging is automatic. Here I can display the file on my directory, so the Tetradecanol. Let's check the masks are good. So here the tool load the last parameter file from the pony determination. I can also display circle. Yes, it seems good. So let's see the last ring. Yes. Here, good. And let's see if the direct beam corresponds. Yes. So now I can also try to do the radial averaging. If I click on absolute intensity, this tool will try to extract the data stored in the EDF file from the Xeuss instrument for the transmitted flux and the incident flux and exposure. Process. Okay, it's done. So good. So I can show you the calibration at another distance. So I will open again pyFAI tools here. So I will choose another configuration of the Xeuss. So I will take short distance at around 40 cm, and here the calibrant is a silver bayonet. Okay, the detector always the same, and I already defined mask. Okay, wavelengths don't change. Next step. Here the mask seems good for the demonstration. Step. So now I can pick the rings. And I can try to extract all reachable rings. Yes, so this seems good. So next step, and here normally, yes, some lines are displayed on the detected rings. So next, let's see in log, Yes, it seems good. So save as pyFAI. And close. Now again, open radial averaging parameter. So I will import this calibration. Here, you see the distance is 40 centimeters. Okay, the mask, I have to define that. Okay, and save. Okay, yes, close. Now I can check the tool, and we are here at this configuration. Can display the silver bainate. Seems good. Is the direct beam? Yes. So now I can try the radial averaging with absolute intensity process. Okay. Close. Now I have, so here you see on the display, on the plot window, I have the two samples Lupolene and Tetradecanol are the same sample measured with two configurations.
I show you the workflow for the image data processing. The next time, I will focus on the SAXS diagram analysis and the extraction of the size and concentration of nanoparticles.